For thousands of years, humans chased a powerful idea, the dream of turning ordinary metal into gold. Medieval alchemists searched for the philosopher's stone, believing it could transform base metals into precious ones. They failed, not because the idea was foolish, but because they were working with the wrong science. Chemistry cannot change one element into another, but nuclear physics can. The real question is not, can copper be turned into gold? The real question is, what would it take to change one element into another at the level of the atomic nucleus? To answer that, we must understand what an element truly is. What defines an element? An element is defined by one thing only, the number of protons in its nucleus. Copper has 29 protons. Gold has 79 protons. That difference, 50 protons, is everything. Color does not define an element. Density does not define an element. Chemical reactivity does not define an element. The proton number does. If you change the number of protons, you change the element itself. That kind of transformation is not chemistry, it is nuclear physics. Chemical versus nuclear reactions. In a chemical reaction, electrons rearrange around the nucleus. The element remains the same. In a nuclear reaction, the nucleus itself changes. Protons and neutrons are rearranged, added, or removed. Nuclear reactions involve energies millions of times greater than chemical reactions. This is why alchemy failed. Alchemists were trying to use chemistry to perform a nuclear transformation, something fundamentally impossible without access to the atomic nucleus. Is it theoretically possible? In principle, yes. If you could change the nucleus of copper, adding or rearranging nucleons so that it contains 79 protons, you would produce gold. But here's the challenge. You cannot simply add 50 protons, one at a time. Nuclei are bound by powerful forces, especially the strong nuclear force. To significantly alter a nucleus, you must use high-energy particle interactions. This requires particle accelerators, nuclear reactors, and controlled nuclear bombardment. These are not chemical tools. They are advanced nuclear physics facilities. Real experiments. In the 20th century, scientists successfully transmuted elements using nuclear reactions. At facilities such as Lawrence Berkeley National Laboratory, researchers used particle accelerators to bombard atomic nuclei and produce new elements. In some cases, gold has been produced artificially. But here's a critical detail. The amount of gold produced is microscopic, sometimes only a few atoms, and the process consumes enormous energy. The cost problem. Could we produce gold this way commercially? Technically, yes. Economically, absolutely not. Why? Because particle accelerators cost billions of dollars, energy input is immense, the gold produced is often unstable isotopes, and the yield is incredibly small. The cost to produce even a single gram of gold this way would exceed its market value by millions or billions of dollars. Artificial transmutation proves that element conversion is possible. It does not make it practical. Where does natural gold come from? The deeper question is not how humans make gold, it is how the universe makes gold. Gold is not formed in ordinary stellar fusion. Inside normal stars, fusion stops effectively at iron. Creating heavier elements like gold requires extreme astrophysical conditions. In 2017, astronomers observed a neutron star merger known as GW 170817. This event confirmed that when neutron stars collide, they eject neutron-rich matter into space. In those extreme conditions, rapid neutron capture, known as the R process, creates heavy elements, including gold and platinum. Much of the gold on Earth was forged in such cosmic collisions billions of years ago. Gold is literally stardust born from catastrophic events. Limitations of nuclear transmutation. Modern physics allows us to change elements, but nuclear transmutation requires precise control, extreme energy, advanced infrastructure, and rigorous safety protocols. It is not something that can be done casually, cheaply, or safely outside specialized facilities. And it does not violate any known laws of physics. It simply operates at a scale far beyond everyday chemistry. Why alchemy failed, but physics succeeded. Alchemy lacked knowledge of atomic structure. Protons were unknown, the nucleus was undiscovered, the strong nuclear force was unimaginable. They were trying to rearrange atoms without knowing atoms existed. Modern physics revealed the internal structure of matter. Once we understood that elements are defined by proton number, transmutation became scientifically meaningful, but it also became clear how difficult it truly is. What this really means. So, can copper be turned into gold? Scientifically, yes, through nuclear reactions. Practically, not in any economically viable way. Naturally, the universe already does it in extreme cosmic events. Gold is rare not because it is impossible to create. It is rare because the conditions required to create it are extraordinarily extreme. Neutron star mergers, supernovae, high-energy nuclear processes. Gold is the residue of violence in the cosmos. Beyond the myth. The alchemists were wrong about the method, but they were not entirely wrong about the possibility. Matter is not immutable. Elements can change, but the price of such transformation is measured in nuclear energy, not mystical philosophy. In the end, gold is not valuable because we cannot create it. It is valuable because the universe creates it only under extraordinary conditions, and every atom of gold on Earth carries the memory of an ancient stellar catastrophe. The dream of alchemy survives, not in magic, but in physics.